you just saw it's sort of dangerous to ad lib, but I'm going to ad lib. I'm just going to be brave and ad lib a little bit anyway. So, because of the fact that I only realized an hour before this lecture these notes really suck, and I wasn't even going to present this belief state dynamics, but I owe it to you. So, there's many ways to get to this. First of all, we have to figure out how to define Bn, how to recursively define Bn. And once you get that, then you fool around and you get this. And so the thing, but what you end up doing is this. I mean, consider like the probability that xn equals x and yn equals y, given the past. Oh, wait, hold on a second, that's not what I wanted. No, that's not what I'm going to start with what I really care about. Sorry. I'm jumping ahead. So that's my Bn of x. Right? So Bn of x, again, is a random variable because it's a conditional probability, so it depends on my observations. And, and basically, I'm going to stick in the function. I mean, I'm going to use the, here's where I was fretting about notation. I completely understand this is confusing. This is a random variable, but it's a function of the observations, and that's the function, okay? For every y0 up to yn, I can compute this thing using Bayes' rule, and that is a function of data, and that capital Y0 is different than the capital Y0 observed. This is just notation for defining a conditional probability. God, we need like more and more symbols. All right, but you just need to really understand probability to get this. That's why I hesitate to even do it. But then you can use Bayes' rule. This is a probability that xn equals x and yn equals little yn. And then divide by this probability. Okay, I'll kill this. All right, and this is just some junk in a way, right? So I don't care about anything that doesn't depend on x, because in the end I can renormalize. I know that when I sum this over x, I'll get 1. So if I see any term that doesn't depend on x, I can just ignore it, So the denominator, I couldn't care less about that. It's just I'll call this some constant, kn. That's what this is, times the top. And that's pretty easy to do because times the numerator. So just calling the denominator k, kn, or kn inverse. And I'll just go and do this. You see, I'm going to skip a step. It's basically So for this thing on the numerator, given all this data, gives me the most likely place this state will be at time n minus 1. Well, actually, let me just write that down. All right, longhand. That's my guy here. Sum over all x. I'm looking at where the states could be at time n minus 1 times the probability that this thing happens, right? Times the probability of going from, I shouldn't have an x there. So I'm skipping a step here, but what you could end up doing is adding x information xn and then take a conditional expectation again. I just don't want to work it out. So from here to here it takes a couple of steps. All right? And this is something we've worked out because the probability of going from x from here to here, and there's also u. That's all you need to know. You need to know the previous x and the previous u to go forward. And that's something you can write down. So that's my previous belief state. And this is precisely what was written down before. It's the probability u of going from, and that's x minus 1. Arrgh. And then once I know xn, yn is just a random function of xn, which we denoted q, believe it or not. Remember that? But that u, what's u? It's the un minus 1 there. There we go. Okay, so if you go and pick up a book, you'll see that whole thing is defined to be rho n. Is this whole big mess over here. Yep.
It is beyond the function of u minus 1.
What's that?
It's beyond the function of u minus 1.
No. Remember the definition of Bn, right there.
Do we need to marginalize u minus 1?
Yeah, it's too bad. It's because I skipped a step, it's not obvious. That's the trouble. I know this is not complete. There's a step here where I have to throw in extra information. I have to put in, as well as my observation, stick in xn, and then take the conditional expectation given yn to get to this, So or xn minus 1, I mean. So I skipped a step, I'm afraid. The notes will be completely complete. And actually, see Hayek. I mean, it's beautifully done there. In fact, I don't even need to. I don't need to give you new notes. Hayek does it very, very well. But this is what you get. But this is so complex, it's ridiculous. So what you usually get is you just take all of that and you give it a name. yn. And again, the reason for suppressing, you only write this as a function of xn and xn minus 1, because you no longer treat un minus 1 and yn as variables. I've observed them, I plug them in, that's it. So you just think of them as stuff you've gone in there, and that little n there is just to capture the fact that you've plugged in your observations. And then you go through and you say, well, all I'm doing is taking some sort of dot product here with that row n there. And hold a second. I have an n minus 1 there, and there's not there. Everybody just, let's see, oh, there's a sum. Oh, there it is. There's the xn. But you notice my x turned into an xn there. We might as well be consistent. Or consistent the other way, whatever you like. That looks more consistent to me. All right, so basically, again, I called all of that row but I've thrown away a constant, and so I just normalized to make sure I get a probability. This constant, we could go and compute it, but why bother? We know, again, when we sum over x, we're going to get 1. So we just force that constraint to be valid, and it gives us kn, so we don't have to compute it. And that's what I'm doing here. I'm taking my numerator, which is a function of xn, and then I'm summing over, like xn prime, if you like, to make sure that this whole thing is a probability mass function. Yeah. And that's it. And that is some crazy function of the previous guy and yn and un minus 1. That's the notation I'm going to use. We've got some mapping from the previous belief state, observation in U to that. So at this stage, you see this and you say, well, where's the controlled Markov chain? All right? But this is called the nonlinear filter. All right. Okay, cool. So what about that crazy thing, Markov property? How on earth would I do that? And before I do that, any questions? So I guess, again, I skipped a step here. You can find in Hayek a beautiful reference. That's the nonlinear filter. Just take it for granted. But how on earth would you go through now and claim that Bn is a controlled Markov chain? It sure isn't obvious, right? Yeah, because it almost looks like it, right? Because you've got the new state is a function of the old state and an input, but it's supposed to be IID noise. It's not IID noise. But yn at least, we know, is a function of ID noise, so that's a hint. Remember yn, I called it G of xn and I don't know what I called it now, W. So that's ID, and that's something funky. All right. All right, so we all got the energy to do this? Shall I be honest, strong, and so I've taught this course forever, and every time I teach the course, 24 hours before this lecture, I say, shit, I forgot to check, do a literature survey, whatever, to explain that Bn is a controlled Markov chain, because I don't know when it happened, but at some point in my lecture notes or something, I had Bn and Yn being the controlled Markov chain, which is true. So you take the Bn and the Yn together, that's a controlled Markov chain. But if you go on, say, go on Wikipedia after this lecture, type in Palm MDPs on Wikipedia, you'll see they'll say, no, Bn is a controlled Markov chain, and here's why. But what they write down is gobbledygook, because they have the Y right there. That's not a controlled Markov chain, right? This is not a controlled Markov chain. You all agree, right? You have to have an IAD process there. So it takes it takes some work to see this as a controlled Markov chain. And I know it's in books by Ritzikas. I have to go into a literature. The trouble is that every time I get to this part in the course, it's less than 24 hours before I give it. And then after this lecture is over, I get busy and forget to do a literature survey. So I'll give you references later on. This time I'll really do it and find some history. So anyway, let's do it though. Let's go and give a very precise proof that actually this is Markovian. So how do you do that? So the simplest way to do it, so there's going to be a theorem in these notes. Okay, so what I claimed before, I'm now going to prove that Bn-Un is a controlled Markov chain. So Bn is the state process and Un is the input. So you could also append Yn and say that's a controlled Markov chain with input Yn. And in fact, it's easy to prove this, and then this follows. Okay? And the way to see that is to, I guess I need all these notes. So I don't need any of this, Let's just do it. So take any set S. These are the sets in the simplex that we'd like to look at probabilities of transition, right? We want to be able to look at the probability. So I'm going to look at this guy here. So to prove the Markov property, this is stronger in a way that, well, no, it's not stronger. This is exactly what I wanted to look at if I wanted to prove the Markov property for the pair process Bn-Yn. Because, really for the Markov process, I should look at all the Y's up to time n and all the B's up to time n, but the Bn's are a function of the Yn. So this is all the information up to time n. And so I need to show, one, that only depends on Bn, the previous B, previous Y, and the previous U. And I've got to give you the formula for it. All right? But then you go through and look at this thing. Once somebody's told you what the next Y is, what's given there, I'm saying Yn plus 1 equals Y prime, you're kind of stuck here. There's only one possibility for B. There's an indicator function here. So Bn plus 1 is right there. Oh, sorry. Yeah. That's great. All right, so if this is Bn plus 1, if yn plus 1 equals y prime. So if this function is not an S, then you just get a 0, it's over with. And then you've got to look at this probability that yn plus 1 is y prime. Okay, and now you know how to compute this, right? And again, I'm skipping the same step. Maybe I shouldn't. Here's the step I skipped before. Okay, sorry for being lazy, but that's what I skipped before, is that basically what you do is you stick in more information and then you condition that away. Again, it's the Tower property. It's the fact that a conditional probability is just a conditional expectation, you know, of an indicator function, the indicator function of this quantity. Okay, and then that, you know, you know how to do is because yn is irrelevant if you know xn. So this is, what is it? It's, let's work it out. It's the expectation of we don't care about that anymore. Well, we do care about that because it has our yn in it, a un in it. So we care about the un. So it's the probability that yn plus 1 equals y prime, given just xn and un. So from there to there is just the controlled Markov chain property. The fact that all I need is xn and un to predict the next stuff one step later. And this inside, let's stick inside first, is a summation over x prime of the probability un of going from xn to x prime, and then our q of y prime given x prime. And I still have to take a conditional expectation. Right? Everybody with me?
Where'd the Q come from?
That was my, so I'm basically I'm looking at the probability of hopping to a new state, and then given my new state, that's the probability of the new action. So this whole thing.
So I thought the PU matrix was the controlled transition.
Now remember, the probability that yn plus 1 equals y prime given xn plus 1 equals x prime. That's why I called Q. Yeah. So that's what I'm doing here. I'm saying I'm looking at all possible next place I can go to. Probability of going from xn to any x prime. And then given that new state, the probability of seeing y prime. Okay? All right, so this whole thing is just now a function of xn, and you get rid of that with the belief state at time n. I don't care about that either. All right, so almost there, everybody. It's right there, isn't it? Okay, so now I've got one random variable xn, and this whole thing is just a function of capital Xn, and I'm taking the conditional expectation given yn, that's where bn of x comes in. So I have a sum over x prime here, now I'm going to sum over x as well. And so I've got this whole mess here. And what's missing is the probability of seeing xn equals x. Right. So right here, again, I'm taking the conditional expectation of function of xn given observations up to time n. We know how to take conditional expectations of functions. We take the sum over all x of that function of x and multiply it by the conditional probability of that x. So there it is, some big horrendous mess. All right, and there it is. So basically I start out conditioning on everything, and in the end, this conditional probability only depends on the previous belief state, and that's it. So where's my transition matrix? So basically that proves this, that the probability of this only depends on the previous state, because it only depends on Bn. Yn doesn't appear. How about this? How do you prove that's what's the transition matrix for that guy? Stare at it. Come on. So how do you go from here to here? Remember, y has to be something, right? Y has to be something. So if I sum over all y primes, I'm just ending up replacing this by the probability that yn plus 1 is something. And so it's just the sum of this. Just take that and stick it in. Yeah. And there it is. Yeah. And so yes, QED. Now it's not that bad, right? I mean, the thing is that, of course, there's a sum over x and x prime, so that could be millions of states. But we lost something. If we lost the indicator function. Sorry, that's what you're going to ask. Remember, I went through I took the last term, I forgot the first. Hold on. So m of Bn y prime and un. So I'm saying is it's not that bad. At least we're not integrating or something. We're just taking a finite sum, and then we just basically have a penalty here. There's a logic function there. So it's not as bad as a horrible integral. So you had a question, or was it? I mean, you had a question just about
Maybe is it the same to condition on yn instead of bn? Like if you want to prove BNUN is a control Markov chain, should we condition on BN?
Yes. Yes. So that's what I was saying before. So let's do that. It's possible it wasn't clear. What I was saying before is that if I want to show that first of all, the joint process BNYN is Markovian, what I should really do is look at this probability, in one-step probability, given the entire history of the y's and the b's. But all the b's are functions of the y's, so it's redundant. So we don't need that. It's irrelevant, right? Okay. And so then when we sum over y prime, then we're actually looking at more information, So it's actually stronger than the Markov property. We're saying that the probability that Bn plus 1 is, when I sum over y prime, I'm saying that, in fact, let's write it down. So the probability Bn plus 1 is in S, given all of Yn is equal to is this function, so this is much stronger than Markov property because Yn could be much richer than the Bn's, So I've got this big sigma field, and yet even though I'm conditioned on some huge sigma field, the whole thing ends up just being a function of two little things, So it's quite strong. And so you can implement this, you can go and you can apply value iteration, and at first sight, you see, this is going to be 0 most of the time, and basically, see, Bn's a random variable, and it's a discrete random variable for every n. At least if B0 is degenerate. And that happens just because of the dynamics. Oh geez, we erased it. It's just the fact that if Bn takes only a finite number of values, you have a discrete distribution, and Yn only has a discrete distribution, Un. So this function of that data only takes on a finite number of points. So you could, in principle, you could just update value functions based on the support of Bn, but that grows geometrically fast. So you're better off binning or something like that, or using a neural network or something to fit a density or something, something like that. Yeah. All right. Okay, but again, philosophy. So what's done in practice? What's done in practice is you say, screw this. I don't even know this anyway. I don't believe this model anyway. I'm going to come up with a belief state, and then I can use deep state for real. Just call it a state, and then run my algorithms and somehow try to learn a model that fits the observations or something else. That's what's done in practice. So I don't think this is used like this very, very often. I think most of the time, again, it's inspiration. You pretend it's Gaussian. You have some problem, and you say, I don't know. This is too complex, so I basically fit some family of probability distributions, and pretend that my belief state is Gaussian, exponential, whatever. Or we're in a discrete state space that's in a, it's you know, some simple family, and then you try to estimate those parameters. That's, you know, something like that. But anyway, this leads to hacks. That's it. You don't use this in its pure form. That's all I want to say. Yeah, but yeah, and I think there's, you know, I think it's still virgin territory. I think there's a lot to do here in terms of research. But that is enough, I think, unless there's questions or no. Yeah. Yeah. All right. So have a good spring break, and I'll get feedback on the exam as soon as I can. I'm traveling all week, but I'll still do what I can. And if anybody has any concerns, contact me, and we'll chat. All right. Anyway, happy spring break.